because there's many mechanical properties. First one is friction, next one is adhesion, and then we have a series of elastic as well as viscoelastic properties. And then there's also some plastic behavior. So I listed them out here, and in the rows, I listed out a number of modes. These are not all the modes that one can do with an AFM, but it's I would say the most common one, and maybe also some more for historic reasons in here. The modes themselves are typically in mechanical or other modes, other property mapping like electrical, are typically looked at as contact modes, resonance mode, referring to the cantilever that is maybe oscillating at its resonance, natural resonance frequency, or off resonance, which typically means a resonance below the natural resonance. We'll go through in this webinar through some of these, not all of them. We'll start with tapping. So one of the resonance modes, one of the historic, very important modes for topography imaging, which also allows to do some mechanical mapping. We'll also look at torsional resonance mode, where we have a resonance that instead of normally will be laterally. We'll skip contact resonance, although I think there will be at least one example in this presentation. And we'll switch to force distance spectroscopy. So these are single point force measurements or mechanical measurements, which are used to extract quite a bit of mechanical properties. There's both force distance spectroscopy and nanoindentation in this group. And we'll finish with imaging modes, where basically we use that point spectroscopy as sort of a mapping manner to map out the mechanical properties in samples with higher resolution. Finally, we'll look at nano-DMA, where in addition to the other mapping mode, we will also introduce the measurement of viscoelastic properties. So I'll start with the tapping mode. Tapping mode is a very powerful method. It can obtain extremely high resolution and can do that quite fast. It's one of the fastest, if not the fastest, AFM imaging mode. When we do tapping, we typically do an amplitude feedback, but we can also collect that phase image. The phase image is actually a very sensitive measurement for variations in material properties. And often those variations are of mechanical nature. So if you look, for example, here at a sample that has 3 components, we can nicely recognize those 3 components in the phase image, whereas they're not really visible in the topography image, which is focused on surface morphology and roughness. The phase image here shows, in this particular case, the carbon black particles as pretty bright, the polypropylene matrix, and the EPTM, the rubbery areas as well. And within those areas, even we see some variation as well. What we don't really know is if those variations are related to differences in stiffness, modulus, adhesion, or who knows, maybe even the electrical charge. It could be any of the above or a mix. And that is often the challenge with phase imaging. This is another illustration of that. This is a block copolymer where the phase image shows an extreme sharp contrast, but it's a little hard to tell where that contrast originates from. Although under certain conditions, we can relate that back to one of the properties, for example, the loss tangent. There's another, I'll call it a challenge with tapping mode imaging, is that tapping mode imaging, in particular the phase image, can be highly dependent on some of the operating conditions we're using, some of the parameters. And this is maybe a little bit an extreme example where we go between 2 regimes, which we call light and hard tapping. We basically modify the amplitude set point or the amplitude, the drive amplitude in a big step. And we see that gets reflected in a change in topography, mostly basically a step change. But in the phase image, we see even bigger changes, including some contrast reversals. So if we start to think of translating those type of phase images into adhesion and quantitative mechanical properties, parameters will obviously be a very important condition and might actually be a showstopper. So I'll move from tapping mode imaging, and you see there's a lot of modes we want to cover. I won't go into too much depth in any of them, but we're happy to do that offline or afterwards if somebody has specific questions. Switching to torsional resonance mode. In torsional resonance mode, we oscillate the tip at its torsional resonance frequency, which basically comes down to a lateral motion of the tip. Typically, that motion is done such that it's a very small amplitude. We're talking angstroms to a few nanometers of amplitude, because we don't want too big, because that would impact spatial resolution. When doing that, we actually have a similar interaction mechanism as we have in tapping. Is we can do, again, amplitude feedback, for example, and collect height images, and again, monitor the phase. The phase in this case is a little bit different, though, in that as the tip is moving laterally, it becomes sensitive also to anisotropic effects in the sample. In this particular example, we can see that, whereas the domains, if I call them, in the tapping mode phase image have a uniform phase signal, they do take two different levels in the torsional resonance related to the orientation of the specific domains. There is an interesting way to operate the torsional resonance mode, is that rather than using that torsional resonance for a feedback, if we use the classic contact mode feedback, basically the deflection of the cantilever, but still use that torsional modulation to monitor its amplitude and phase, we can actually get access to the mechanical properties, and in particular the friction, or what we like to refer to as dynamic friction. This is a sensitive method to measure the friction, as you're actually operating at the resonance to take advantage of the higher Q factor, the higher quality factor, the higher sensitivity. This image here shows a carbon fiber embedded into epoxy, and the torsional resonance phase image nicely shows that contrast, mechanical contrast related to friction. As is a resonance technique, we can also consider to add a phase lock loop control to this, which basically will shift the frequency until the phase becomes zero, sort of a phase feedback loop, and display then the phase image, the frequency images, which is shown here on the right. The interest of doing that could be that the frequency image could give you an even better signal to noise than the phase image. Again, as a dynamic friction. Very recently, there's been some very interesting work by Mihir Pendarkar at Stanford University and the group there, and as well as some collaborators. The work was done on 2D materials and is published in under torsional force microscopy of van der Waals, moraes, and atomic lattices. What we're looking at here is a morae pattern which has a 2.6 nanometer period, and we also see the underlying atomic lattice of the graphene. So this is a very nice illustration that this torsional resonance, or call it dynamic friction mode, can actually go down to an extremely high resolution. So leaving the resonance modes behind, we go to point spectroscopy.